I think I'm going to get started. So welcome everyone. Thanks for coming along to the Neo4j deep dive track. Well done for making it down from the 3rd floor. In this room we're going to have a series of talks that are quite technical and like go into some details of the features in Neo4j and how it works. And today I'm talking about causal clustering and our clustering solution. And it's particularly the features that Philip was talking about this morning in the like what's new in 3.2. So I'm if my pointer works, great. Oh, I think I know what's wrong. There we go. There we go. So I'm Alistair Jones. I work in product engineering at Neo4j. And today we're talking about clustering. What clustering means for us at Neo4j is putting Neo4j into a data center. Is putting it on lots of servers, like this Google data center here, or lots of Neo4j. That's what we're going for, lots of Neo4j everywhere. Let's talk about why we want to do that. So clustering, there are a few reasons why people want to have lots of servers. The first one people probably think about first is to have a lot of throughput. So you're running a massive website, you've got lots of users, they're doing stuff all the time. You don't want to queue up waiting for one little server to do its job, so you want to spread the load across a load of servers. That's the first thing. Secondly, you probably get into worrying about redundancy, about losing stuff. So if I've just got one server and then something unfortunate happens to that server, like it catches fire, then I'm going to lose all my data, and that's a really bad idea. So to get redundancy, I start off with a group of servers. They all have a copy of the data, and so if one of them dies, it's dead, but I've still got the data saved somewhere else. The third thing that people are using it for is high availability. So this means that I want to maintain my service even when something goes wrong. So the same situation with one server, it goes wrong, it crashes or it catches fire again. I'm going to show my users an error page. Even if I've got a backup somewhere, that's not good enough. I need to have that server actually available. So what I need for high availability is I need some kind of switching. I need to be able to switch over, fail over to another server so that I can maintain service. So if we look at all of those together, I can summarize them like this. We've got high availability, we've got data redundancy, and throughput. And all of the clustering stuff that we do is about addressing those three needs. Now, Neo4j has been around for a long time, and we've had clustering for a long time. And actually, we already do a lot of this stuff. We've done it for years. Back in Neo4j 3.0 is where I'll start. We had some level of support for all of these features. But in 3.1, which we launched late last year, we added a whole load of new stuff. And I'm going to kind of go over some of that stuff from last year. So we put in, on the high availability side, we put in built-in load balancing that makes it much easier to fail over between the servers. For redundancy, we did a massive piece of work on consensus commit, on using, like making sure that we save to a majority of servers. And on the throughput side, we put in support for much bigger sizes of clusters, larger clusters. Now today, we've launched 3.2. And actually what we're doing is extending all of those areas with some more features. And Philip talked about them this morning in the room upstairs. I'm going to go through those through those features as well. So this is the structure of the talk. You know what's going to happen. We're going to go through basically those 6 areas. First of all, let's start with the load balancing. So this is my picture that kind of explains. We're going to use this picture a lot, so I hope it looks okay on the picture. Hopefully this makes sense to everyone from a kind of architectural point of view. This is one of the ways that we think about how people use Neo4j in an online application. So at the top, we're thinking about end-user devices. So what I mean by, oh, that's working. So what I mean by the end user devices is mobile phones, web browsers, something that a real person is going and using your application. What they actually connect to is probably not directly to Neo4j. So probably you've got an application running on some kind of application server, and you've written it in some application programming language in Java or Node.js or something like that. Ultimately, the application servers talk to Neo4j, and Neo4j is where the data is stored, where you run queries and traverse the graph. What I've tried to show with these like sort of spotlighty bands going on is that there's communication between all these layers, and that it's balanced. So when you're using a mobile phone, you don't talk to a specific server. I don't have to name a server. I'm just going to go to google.com, and it's going to direct me to one of the application servers there. Similarly, we want to distribute load. We want to balance load across the database servers, and that's what's going on. That's what's going on between the application servers and the database layer. So how do you achieve this? There's lots of ways that you could do this, but what we introduced in 3.1. What we introduced from 3.0 is we started supporting an official set of language drivers. And that's what I've shown here with the orange bits. These are bits of code that are running on each of the application servers. It's the driver, and you can think of that as being kind of part of Neo4j now. It's another part of the database, but it's running on your application server. So there are official supported drivers in Java, JavaScript, .NET, and Python. So if you're on any of those platforms, you have the official driver. Also, we'll be extending that to other languages, and there are also already community supported drivers on other languages there. How does this factor into the load balancing conversation? Well, in 3.1, what we did was take on some of the load balancing responsibility into the drivers. And we did it with something called, we're focusing on this area, we did it with something called bulk plus routing. So you recognize the way this is written. This is like a protocol. So how you write HTTP colon or HTTPS colon at the beginning of an address. This is a protocol for talking between your database driver and the database. So this is how you use it. If you're in your application, you can create a driver using graph_database.driver, and you pass in a URL. You come from your config somewhere. If you're developing on your laptop or you're testing, probably you just use the bulk protocol. And the bulk protocol goes straight to that server. You know exactly where it's going. It's a direct route in. With bulk plus routing, you just have to change the URI, and your application should just work. The idea is just works the same way. But actually, behind the scenes, what it's doing is it's using this server address to just ask that server where all the other servers are. And then from that, it can construct the routing table and route requests across all the cluster of servers. And you can do fancy things here with having a DNS entry that corresponds to many of the servers, so that all you really need is to discover one that's currently deployed. So how does this practically work? What effect does this have in the routing? It's a situation you need to look at is what happens if what happens if one of the servers fails for some reason, like that catching fire or going wrong. So here we've got a server that's gone red. There's something wrong with it. Maybe the lovely cloud provider has shut down your host and it's not available anymore. What impact is that going to have? Well, on this picture, I've shown like these application servers happen to be connecting to this one, and they're not going to work anymore. They're going to fail because that server is not there. We've distributed the intelligence around this so that the cluster itself becomes aware of that missing server, that server going away, and it means that it can update the drivers with their routing information so that they can route around this failed server. Similar case if you add a new server into the cluster. This is how you discover it's there, is the cluster itself becomes aware of the new server, and then it will inform the clients who are connecting to it, so yeah, here's somewhere else you can send your load. So introduce this mechanism in 3.1, and it's a nice way of distributing the load without any special infrastructure. You don't need your own load balancer or anything. You just deploy application and database. That was load balancing. Let's look at where we've extended this area on the high availability side into transaction functions. Now, I wonder if that makes sense to anyone, what that might be. It's basically applying what you might have heard of as called a unit of work pattern. So this same picture again with a failed server. It was all good because we repaired the routing, but the problem is at the point where the problem we're trying to address is at the point where this server fails. Those requests, the actual request that's running at that moment, is going to fail, and we suggested to users this to have a retry, in your application, which works fine. You just try the same thing again. But writing retry logic is not super easy. But you need to get it right. So we've tried to make it a bit easier for users of the driver by providing a built-in retry capability. So we've just built that into the API, and it looks like this. Can everyone read this? Okay, by the way. So contrast. Okay, cool. Basically, what we've got here is this syntax here is the Java syntax for a Lambda. The same thing applies in languages that supported this for years. You can use a similar thing in Python or in .NET, where it's a little function the driver is going to call back when it's got a connection with a transaction open with the database. So you can do whatever you like in there. If it goes wrong because that server's gone away at that moment, it will just retry automatically, potentially having refreshed the routing information. So it discovered where it should be going, and it will route the traffic over to that location. Right, so this works out really well. I think this is going to make applications really simple to write. You can see how little code that is to do something with the database. Okay, so applying it is going to, the server fails, immediately it's going to retry, and you're going to get it, here we go, retry, and then it's going to succeed. Great. Cool. Just a note, if anyone's got any questions, I'm going to try, I've got a little bit, I'm going to try and keep going with the time. So what I suggest is that we keep the questions right to the end, and I might actually make room for the next speaker, and I might go outside. So that might be the best place to catch me in a huddle just at the back. Might be a good way to go. Cool. Let's go on to the next area, which is in data redundancy. How do we deal with that? Consensus commit. So what we did in 3.1 is we implemented a consensus commit protocol. The diagram on the left is trying to explain what that means. It's basically saying whenever I do any kind of write to the database, I want it to be on a majority of servers. And that means that there's no possibility of divergence. Like I can't have sort of two different versions living in the cluster elsewhere. I can't lose data. And I also don't have to wait for the slower server. I've got a really slow server or one that's far away. I don't have to wait for it. And to achieve this consensus, to build this feature, we used a really nice protocol from the research community called the RAF consensus algorithm. It's really fun, this stuff. It's really interesting stuff, and it's definitely like the cutting edge of consensus at the moment. I'm going to try and explain it in very, very quickly. What's great about it is having, because it's got an active research community around it, you can get little animations to help you to understand how it works. Briefly, it works using a consensus log. and the whole algorithm is based around electing a leader in the cluster and then safely agreeing each transaction in the log. But it's a great algorithm for this kind of stuff. And we integrated this deeply inside the middle of Neo4j. So when you do a write, it's safely written to the first server that you hit. That may fail before that server might potentially disappear before the transaction is considered committed, but that's a fine situation. The whole protocol is designed to cope with that. Eventually, we get into, well, the middle part here, we get into the Neo4j transaction log, which we've had for years, that same kind of structure, and eventually you get persisted into the graph. Cool. So what do we do to build on a consensus commit? Well, let's think about multi-data center. So why do we need the multi-data center? Well, this picture, remember like a server catching fire? Actually, it's pretty likely that this happens. That's really bad. All your servers catch fire at the same time. Why is that going to happen? Well, what if all your servers are in the same room and the room catches fire? You lose your data. That's not a good idea. How do people deal with this? Well, there's lots of ways of dealing with it. Commonly, if you're using Amazon Web Services, for example, you probably use availability zones that are close to each other in the same region, but are somehow guaranteed that they won't simultaneously fail. For the moment, we're going to look at a different solution. A different option works kind of the same way. It's just to spread your data centers out around the world. And so this is a multi-regional deployment. And we could call them US, Europe, and Asia Pacific, for example, is where we could put our data centers. How does that look in Neo4j? Well, it's pretty simple. We just have a cluster, and we say these servers on the left are in the US, the servers in the middle are Europe, and the ones on the right are in Asia. Easy. And this works already. This works with 3.1. You could have a cluster that was spread around the world, and they'd all talk to each other. But there's a problem with it, and the problem comes in this area here, I've highlighted in blue, is that sometimes you're going to get a connection from an application server to a database that are in different regions from each other, and that could be quite low. That could be quite high latency. It could take a long time for the electrons to travel across the Atlantic or Pacific. So that can distort the performance of your application. So what do people really do about this? Well, what they do is they do affinity in their data center. So they align with a specific, they align with a specific region, and they want it to look something like this. We've added support for how to do this now, and how you do it is in the config file, this is neo4j.conf, you can set a group that identifies a set of groups that I think this server is going to be in. So this is an American server. I say group equals US. I then create a policy that says route stuff to the US servers. And then in my client, I can attach this to the URI. Remember, we use bolt plus routing. I can just stick another bit on the end and say policy equals America. Now, requests from that server are going to go to the US servers. Make sense? So putting that into the picture, we've got America at the top, US at the bottom. And those two, you see now no crossing, no blue lines, no crossing across the oceans. Similarly, in the other regions, I can do Europe and EU. And then across all the servers, I just do this mapping from America to US. You might think it's a bit complicated. Why have I got different US versus America? Why don't I use the same name? Well, you could use the same name, but you'll see there is some more sophistication you can put into this. Let's look at this problem. What happens when the whole of the US data center, something goes wrong with it? In the current, the configuration we've done so far, what would happen is it would fail over and start distributing to the whole group. That's the fallback position. Could you do better than that? Yep. You could say, actually, second best is Europe. If I can't do America, I'll do Europe. And we can support that in the configuration as well. So a new policy, America first, that says go to the US, but if not, go to the US and Europe. And what that practically means, it's quite a sophisticated thing. First of all, go to US, so long as one of them is available. If there's none available, then we try US and EU. Probably it's just EU, really, because the whole of the US is unavailable. If none of those are even available, then finally I fall back to the Asia-Pacific. It's even more clever than that, because it's even more complicated than that, because what happens if there's kind of an edge case we worried about is what happens if there's just one server left hanging on in the US. We say, oh, we've got a US server, so let's just hammer it with all the traffic from the whole of the US. That server could become overloaded. That's this little exclamation mark. Can we have a policy for that? Yes, there is a config for that. We can do US, but a minimum of 2 in the US. If there's less than 2, then I fall straight back to the US and Europe. Cool. So, so those are the built-in things. That's a little DSL I can use to define my strategy. You may know a lot more about this than we do. We want to build more sophistication into this in the future. If you already know how to do this balancing, you've got a more complicated setup. You can write Java code and just plug into an interface. We'll drop it in a jar file. We'll pick it up, and you can have an arbitrarily sophisticated load balancing policy looking at your own monitoring, and you don't have to change the drivers. It can all live on the server side. So that's pretty powerful if you've got a really complicated deployment you want to do around the world. Okay, let's move on to the next area, large clusters. Okay, so the first thing about large clusters, this observation I think is really crucial for graphs, is that there are there's two things you do to the graph. You update the graph and you read from the graph. What we've noticed with what people do with Neo4j is they tend to do quite local updates, small numbers of nodes and relationships per transaction. But when they read, they're doing massive recommendations, they're pulling in whole sections of the graph, hundreds or thousands of traversals in that single query. And that means actually what the constraint, it's quite low amounts of CPU and resources that you use on the write side, but you use huge amounts on the read side. So the priority for having a large cluster is often to have a lot of read servers. And that's what we've designed this architecture for, is to make it really easy to have loads of read servers. So we introduced these things called read replicas. I've colored them green here to distinguish from the other stuff. And the core is the ones that do the writes. They do the consensus. What's great about these is they don't have participating consensus. So I can add more and more of them without slowing the writes down and without worrying about availability. They're suitable, so they take the read traffic, and they're suitable, this is how you configure it, they're suitable for adding more and more of them. So that it's ideal for elastic auto scaling, for example, is a perfect thing to use with the read replicas. I just want to call out one bit about it, and this is, so hopefully I'll be able to explain as well. You might have noticed this kind of, you might have gone, what the hell? It says eventually consistent. That sounds really bad. I just want to, so side diversion into consistency. Has anyone seen this problem before? You are buying something on your phone, you need to log in. So you're like, great, I will create an account. You might recognize this name. I create the account, then I go and log in. It's not there. What the hell? I just created the account. How does this happen? Well, a few minutes later, it does work. What's going on? This is something that you can see in with eventual consistency. It happens when you go to a different server the next time around. And I kind of show it in the database is that this on the right is the state of the graph. When I created the account, it created this extra node on the right, but it doesn't propagate to all of the servers by the time I go to do my login. So I get a failure. We've got a solution for this, which we call causal consistency. It supports causal consistency. And this makes it much more practical to work with eventually consistent replicas in the system. basically what we do is wrap a token in a little string that you can keep in the driver or even send right out to your end user device. And when we do it again with this bookmark, we still have the same situation, the server's behind, but the server waits the few milliseconds until the data that's updated in the core is propagated to that server. So you never see this gap. It prevents you from seeing the gap between the servers is the point of it. And we've done it for the point of view of that user. It's the causality of what the user did that defines the dependency between the two transactions. Cool. So I'm going to, the last area we're a little bit tight on time. So tiered replicas is the last thing we did. We tried to reuse that multi-data center stuff and use it for the replicas. One of the problems that could solve is, it doesn't really show on this diagram, but if I had loads and loads of replicas, like thousands of replicas, but only a very small number of core servers, I could actually overload the core servers trying to push out the updates. So the tiered replicas allows you to define like tiers of replicas, and using the same selection strategy as we had for the multi-data center usage. So I can say, you get your updates from this particular location. Cool. So that's the whole. Oh yeah, it's just showing how that works in the configuration. Cool. So that's a very quick run through of all those features in those three areas. And just a reminder that it's these transaction functions, the multi-data set, and the tiered replicas that are the new features in 3.2. If you want to go and check this out, the documentation is all up there. It's all described in a lot of detail. So hope that takes you through how this all works. And it's available right now. So brilliant. And I'm going to make way for the next talk, but I will be just outside, and I'd be very happy to chat through how this works and answer any questions you might have. Thank you very much.